Uh, Good evening, one and all. Today we have parallel technical session 22nd in Hall B. We have total 5 presentations. After the state of the art practice lecture delivered by Professor Brady from Utah State University. And for this technical session, we have chair and then co-chair. And it is my pleasure to introduce for this technical session our chair, Dr. Vijayendra. Dr. Vijayendra is a senior professor in Bengaluru Institute of Technology. He obtained his BE degree in civil engineering and ME degree in geotechnical engineering from University of Visvesvaraya College of Engineering (UVCE) under Bengaluru University. He completed PhD from National Institute of Technology, Surat, and is a member of several professional bodies, including Indian Geotechnical Society and the Indian Society for Earthquake Technology. He is currently teaching at the Department of Civil Engineering at his own parent institution. As I found him, he is a very active researcher and a very interesting personality. He is an excellent teacher and he is having research experience for nearly 2.5 decades. And his areas of expertise involve soil dynamics and earthquake engineering, ground response studies, and seismic hazard analysis. So on behalf of the organizing committee and on my personal behalf, I invite Dr. Vijayendra uh, to chair the session for this event. Vijayendra, I welcome you to chair the session.
Thank you, Professor Govindraju, for that kind words and nice introduction. We have this session on the third day.
One second. I have to just a minute. I have to introduce co-chair. I will invite. Yeah. Now it is my pleasure to invite our co-chair, Dr. Chandra Bogi Reddy. I would like to introduce him to the delegates who are present here. Dr. Chandra Bogi Reddy is assistant professor in the Department of Civil Engineering of Geotechnical Engineering Division at Vardhaman College of Engineering, Hyderabad. In the year 2019, his PhD degree was awarded, titled under the thesis Rapid Assessment of Compressibility Behavior of Clay Soil from Experimental and Finite Element Simulations from Civil Engineering Department, SVNIT, Surat. He received 2 Best Paper Awards in the National Conference and also he delivered 10 guest lectures in various national level seminars. He is associate member of I.I.Sc, 7ICRAGEE, MI, and then life member of Indian Society of Earthquake Technology, life member of ISRMTT, and fellow of FSIESRP. So with this brief introduction, I invite Dr. Chandra Bogireddy on behalf of the organizing committee to chair this session.
Thank you so much,
Chandra Bogireddy, please, I welcome you to chair this session.
Thank you.
Before start of the session, it's just like a small information to chair and then co-chair. Organizing committee has decided to identify the best paper presenter award only from the students stream, and then out of the presentations, the chair and then co-chair are requested to finalize one name and kindly forward it to the organizing committee so that the best paper awardee will get a prize, okay, in the valedictory function. So now I will hand over the platform to the chair and co-chair.
Thank you, Professor Govindraju, for that nice introduction. Also, I thank my co-chair, my colleague, and the secretary of the event, Professor Jekka, for giving me this opportunity. And not the least, I welcome Professor Brady or Cox to deliver the state-of-the-art lecture of the session. And also welcome all the presenters today. We have 5 papers. To start with, let me formally introduce Professor Cox. Professor Cox is a professor in the Department of Civil and Environmental Engineering Department at the Utah State University. Prior to joining USU, he served on the faculty of University of Texas for 8 years and the University of Arkansas for 6 years. Dr. Cox specializes in geotechnical engineering with emphasis on issues related to seismic design and in situ characterization of major construction projects. His research efforts combines the experimental field investigation with computational analysis, particularly for high performance computing with subsurface imaging process. He has led teams deployed to collect the seismic site characterization data at the ground motion recording stations, soil liquefaction sites, and structural failures following the significant earthquakes in the US and around the world, which includes Japan, New Zealand, Peru, etc. He has also participated in numerous dynamic site characterization projects for the seismic design of critical facilities like nuclear power plants and others in the US and abroad. Dr. Cox is a recipient of prestigious Faculty Early Career Development Award from the US National Science Foundation and the Presidential Early Career Award for Scientists and Engineers, which he received in a ceremony at the White House from President Barack Obama. He has authored more than 100 peer-reviewed publications and has taught 8 different courses at the undergraduate and graduate levels at 3 different universities. On the personal note, he grew up as a son of a tough and hardworking coal miner in Helper, Utah. His personal life is influenced by 5 important women, his wife and his 4 daughters. He loves all outdoor activities and currently spends quite a bit of time training for endurance sports, having recently completed an Ironman triathlon and 50-mile ultra marathon. So he is sportive, is researcher, active researcher, and a well-known teacher also. And I welcome Professor Brady Cox for delivering his lecture, state-of-the-art lecture on H/V, geostatistical approach to account for spatial variability in 1D seismic site characterization. I request Professor Brady Cox to deliver his lecture now. Thank you.
Thank you for that great introduction. I really appreciate it. It was perhaps too long for everyone to hear, but hopefully it wasn't too painful. I'm going to.
It was interesting.
Good. Thank you very much. Well, it's very early in the morning here in Utah, where I live, about 4:30 a.m. And I know it's in the afternoon where you are. I wish that I could have joined you in person, but hopefully the presentation will still be of value to everyone. Can everyone see my screen before I continue my presentation?
Yes, it is clear.
Good.
Clear.
So I would like to quickly acknowledge my current PhD student, Mohammed Halal, who is still at the University of Texas. All of my slides have this banner for the University of Texas because the work I did was at the University of Texas, and my PhD student is still there. And I am currently at Utah State University. I moved universities about almost a year ago, let's say. So first of all, when we talk about site response, we're studying the amplification and the changes in frequency content of earthquake ground motions as they propagate from bedrock or some reference subsurface condition up to the ground surface. And in order to understand site response better, we found that it's very useful to use borehole array sites. And there's numerous borehole array sites around the world. I've highlighted some of the borehole array sites in California, in the US, and also in Japan. And I'm not sure, you may also have a number of borehole array sites in India as well. But these are wonderful tools where we're able to record seismic ground motions, both at depth and at the surface. And then we can, from those recorded ground motions, we can do predictions of site response and see how well our predictions match the recordings. One of the issues that we found, though, as more and more researchers have studied earthquake recordings from borehole array sites, is that we generally are probably not as good as we would like to be in terms of simulating or modeling site response. And here, this figure presents a synthesis from 5 major research studies, all using borehole array site data, and totaling 662 sites around the world. And basically, depending on the study that you look at, there have been approximately 30 to 80% of the sites studied that are poorly modeled using 1D ground response analysis. And so you can see, for example, this large study published in 2019 by Marco Pils and Fabrice Coton, of the sites that they studied, where they studied more than 200, only 45% of the sites were poorly modeled. And if you look at Thompson et al. From 2012, 82% of the sites they studied were poorly modeled using 1D ground response analyses. So results vary depending on many things, but in general, I think it's fair to say that we are not as good at doing site response as we think. And so these studies collectively challenge the wide applicability of 1D ground response analyses. And while 3D ground response analyses could be used, generally we lack site-specific 3D subsurface models, and also the 3D GRAs are computationally expensive. And these two challenges really prohibit us from performing 3D ground response analyses, at least on a wide scale. So the question then becomes, can we still use 1D ground response analyses, but improve their performance by accounting somehow for spatial variability on a site-specific approach? And today I'm going to talk about a new framework that we call the H/V geostatistical approach. And we can use this H/V geostatistical approach to develop site-specific 3D VS models. We call them pseudo 3D VS models, and I'll show you why later. But it's really a rapid technique that can be performed very cost effectively, that will allow us to incorporate spatial variability on a site-specific scale to be used in ground response studies. It requires only a single shear wave velocity profile. You can use more than one, but it requires only a single VS profile. That VS profile can be measured in a borehole, or it could be developed through surface wave methods. It relies heavily on spatially distributed H/V measurements, and I'll talk about those in just a minute. And then it integrates geostatistical modeling tools to develop the 3D subsurface model. So in terms of where I'm going in this presentation, I'll first discuss very briefly what H/V measurements are. I'll then talk about the geostatistical approach we use for developing the subsurface models. And then I'll show applications at 2 US borehole array sites, the Treasure Island downhole array and the Delaney Park downhole array. And then we'll talk about the implementation of the 3D subsurface model in ground response analyses at both of those borehole array sites. And then we'll compare this new approach, the H/V geostatistical approach, with standard methods that people use to account for VS variability, such as shear wave velocity randomization, and then I'll provide some concluding remarks. So first of all, an overview of H/V measurements. We use background noise, or microtremors, as called by some, to infer properties of the subsurface. And how we do that is we put a sensor on the ground. That needs to be a 3-component sensor, preferably something like a broadband seismometer. That's typically what I use. You record 3 components of ambient vibration. Once that ambient vibration is recorded, typically for 30 minutes, sometimes a couple of hours, we process the north, south, and east, west horizontal components. We take their Fourier amplitude spectrum, and we divide the Fourier amplitude spectrum of the horizontal components by the Fourier amplitude spectrum of the vertical component. And when we do that, if the site has a strong impedance contrast, and if the records are of sufficient quality, we often see that the H/V spectrum, which is shown down here, often has a peak in it, and sometimes more than one peak. But the lowest frequency peak, we call that F0, or the fundamental frequency. And I have the subscript H/V to make sure that we understand this is an estimate of the fundamental frequency from H/V testing. And that fundamental frequency is related to, using this well-known quarter wavelength equation, to the average shear wave velocity over the depth of the soil on top of bedrock, divided by 4 times the thickness of the soil layer. And so this is a rough approximation, this quarter wavelength equation, but it helps us understand how the stiffness, represented by Vs, and the thickness of the soil, represented by H, control the fundamental frequency of the site, which is a really key parameter for site response. So the H/V geostatistical technique is dependent on performing a number of spatially distributed H/V measurements, and then we extract F0 from those H/V measurements at every single location around a site. And in this case, don't worry too much about the exact size of the area and the number of measurements. It's just a schematic. But suffice it to say, we need to perform these measurements in some locations around our site. And then we're going to use geostatistical kriging in order to change those irregularly sampled H/V measurement locations into a uniform map on a grid. And these grid cells could be every 50 meters, every 100 meters, every 10 meters. It depends on the site, the size, as well as the density of the measurement locations. But we then end up with a uniform map showing the fundamental site period variation across our construction site. We have a measured shear wave velocity profile somewhere on the site. In this case, we happen to show it right in the middle, but it doesn't have to be that way. And again, you could use more than one measured VS profile, but in this example, we're just showing one. This happens to be a shear wave velocity profile that was measured using PS suspension logging. We then need to somehow modify this shear wave velocity profile and scale it so that it's, when we move this shear wave velocity profile from, say, here in the middle over here to somewhere in the blue where the F0 is higher, that this shear wave velocity profile will give us the correct fundamental site frequency. So we're going to have to modify this shear wave velocity profile numerous times. There's multiple ways to do that. You could simply scale the VS. You could increase or decrease the shear wave velocity profile to change the fundamental site period, and then develop a scaling factor. You could also change the thickness instead of changing the stiffness. So you could raise or lower this impedance contrast boundary, and that would change the fundamental site frequency implied by the shear wave velocity profile. You could change both the shear wave velocity and the thickness of the soil, and that would also change the fundamental site frequency. In fact, there are many, many options, and it's really an ill-posed and non-unique process. So we don't know exactly what to do without making site-specific measurements, but to make site-specific measurements at every location is not cost-effective. So what we decided to do in this work is not just scale VS, because that could yield unrealistic shear wave velocities. We decided that, generally speaking, the thickness of the soil deposits are the major contributor to the fundamental site frequency. And so we chose predominantly to scale the thickness of the soil deposits in order to get a shear wave velocity profile that would match the fundamental site frequencies from our kriging. So with that being said, we're going back to this general schematic. We take a measurement of the fundamental site frequency near the shear wave velocity profile of interest, and we develop these scaling factors. The scaling factors are simply the ratio between F naught at the location of the shear wave velocity profile and F naught everywhere else in this grid of this map. And those, then we can get a scaling factor for every cell, and we apply that scaling factor uniformly to every single layer or every single geologic formation in the shear wave velocity profile, so that we scale the thickness up or down in order to match the fundamental site frequency. And when we apply those scaling factors, for example, we can take that single measured shear wave velocity profile and obtain a bunch of different shear wave velocity profiles. In this case, they're color coded to the same colors on our H over V map. So we can visualize the variation of shear wave velocity across our site in 1D, but we can also create 2-dimensional or 3-dimensional subsurface models using this approach. And the reason we call it a pseudo 3D model is because we've estimated the shear wave velocity in 3 dimensions rather than measured it in 3 dimensions. So we're going to apply this method at several US borehole array sites. The first one being the Treasure Island downhole array, which is here in Northern California near San Francisco. And the second one being the Delaney Park downhole array, which is in Anchorage, Alaska. I'll focus predominantly on Treasure Island. And so Treasure Island is in San Francisco Bay, and it's this large island right here. It's actually a man-made island. It was created through hydraulic fill means to host the World Fair, and I believe like 1912 or something like that. It's right next to a rock outcrop called Yerba Buena Island. And so often this is a nice case study for seismic site response, and some of you may have studied it in a course in the past. But this is the rock outcrop, Yerba Buena Island. This is the Oakland Bay Bridge here that goes from Oakland, California over to San Francisco, California. And then this is Treasure Island here in the background. So what we did is we deployed approximately 100 H over V station measurement locations on Treasure Island. It took us only a matter of 2 days. We also performed surface wave testing, so some of the H over V measurements are clustered in groups for large surface wave arrays. But from those 100 H over V measurements, you can see that a lot of the F naught values on this site on Treasure Island are fairly uniform, varying somewhere around 0.8 hertz, maybe to 0.6 hertz. But as you get close to Yerba Buena Island, which is over here, obviously the fundamental site frequency increases and the rock gets, or the response is stiffer because the soil deposits are thinning as you get close to the rock outcrop. So we took those 100 H over V measurements, which are spread out over 1.5 kilometers in this direction, and about 0.8 kilometers or so, 800 meters in this direction. And we used geostatistical kriging to develop a uniform map of site period on a 50-meter cell, grid cell spacing. We then took this shear wave velocity profile, which was measured using PS suspension logging, and it is located right at the this borehole array where we have uphole and downhole accelerometers. And we scaled those 1D VS profiles to match F0 at every single cell. And obviously we can develop two-dimensional or three-dimensional subsurface models using this technique. In the two-dimensional cross-section, I'll point out here, every one of these white markers represents the location of an accelerometer in the Treasure Island borehole array. So once we have this 3D model, if we want to incorporate it into 1D ground response analyses, we're not going to use the complete three-dimensional model. We're going to use these 1D VS profiles. And what we'll do is we'll perform site response for every single one of these one-dimensional VS profiles. And then we'll combine the transfer functions and take something like a log normal median of the individual 1D ground response analyses. And we would call that a spatially aggregated approach to developing a median estimate of the site response. And the cool thing about this, the 3D, pseudo 3D VS model is that we can investigate incorporating different spatial areas. And we can study the site response at these borehole array sites and decide how big of an area do we need to incorporate in order to best match the recorded ground motions. And so in order to study our ability to predict accurately, we're going to use the empirical transfer function, which is a measure of the recorded ground motions at the site. So we'll simply take the deepest rock accelerometer ground motion, and we'll divide the surface output accelerometer by the rock accelerometer, and we'll develop what we call the empirical or experimental transfer function, the ETF. So this is a measurement of the actual recorded ground motion at the site. And then we can use the shear wave velocity profile to do a prediction of the theoretical transfer function. And this is a simple closed form solution for linear viscoelastic site response. And we're going to be using only small strain ground motions so that we don't have to worry about modeling the soil nonlinearity. So here you can see that the theoretical transfer function matches fairly well with the empirical transfer function in terms of the locations of the peaks, but not so well in terms of the amplitude, particularly at the fundamental mode of site response. We're going to judge in this study the goodness of fit between the empirical transfer function and the theoretical transfer function using two metrics. The first is the Pearson correlation coefficient, which was proposed by Thompson et al. In 2012, which predominantly judges the alignment of the peaks in the transfer functions. And that's called the R coefficient right here, the Pearson correlation coefficient. We're also going to use a metric that we developed called a transfer function misfit, which judges a little bit better the differences in amplitude between the empirical and the theoretical transfer function. And so you'll see me in the next slides compare both R values and MTF, or transfer function misfit values. So at Treasure Island, we used approximately 50 small strain ground motions to develop the empirical transfer function and its log normal median. And that's shown here in black. So the black lines are the median and the plus and minus 1 sigma on the recorded ground motions at Treasure Island, small strain. And then the green line is the theoretical transfer function from the PS suspension log. And you can see that it actually does quite well at matching the peaks, but in particularly the fundamental frequency, we're underestimating the width and we're overestimating the amplitude of the site response. So that Pearson correlation coefficient, that R value for the VS profile that was measured in the borehole, is about almost 0.65. Now, when Thompson said that an R value greater than 0.6 means that you're generally modeling the site response fairly well. So Treasure Island is a pretty well-behaved borehole array site. There's been others who have performed site response work at Treasure Island. For example, Afshari and Stewart in 2019, and Tao and Professor Ellen Rathje in 2019. And they both found that by modifying the damping that they use in the viscoelastic theoretical transfer function, that they were able to get R values close to 0.82. So simply by changing the damping, they were able to better predict the site response, because that would bring down the peak and broaden it somewhat. So what we did is we used our 3D model, looking at different areas, to predict the goodness of fit between multiple 1D site response analyses. And when we used an area of 400 meters by 400 meters, which is this area here, which is quite large, by the way, 400 meters by 400 meters is a large site. When we did that, you can see that the amplitude of the theoretical transfer function, the green line, was brought down quite low and better matched the empirical transfer function. So good, in fact, that we achieved an R value of about 0.87 when we incorporated a 400 meter by 400 meter area. The width, though, is still under predicted. So what we did is we decided to increase the size of the area that we considered to be significantly larger. And we kept changing the size of the incorporated area from maybe, 800 meters by 800 meters up to the full size of the island, which is, quite large, over 1.5 kilometers. And eventually, when we included the full area of 1,600 meters by 1,000 meters, we achieved a Pearson correlation coefficient of greater than 0.9. So that's this kind of pink line right here, magenta. And you can see that as we started to incorporate some of the influence of Yerba Buena Island into our ground motion analyses, that we were able to widen this peak, which better matched the empirical or recorded transfer functions. And yet, by doing that, we don't mess up the high frequency predictions. So this is really quite a novel approach to incorporating spatial variability in 1D ground response analyses. And we were able to achieve much better results than any previous studies at the Treasure Island downhole array. One thing I would stress, this then says that the site response recorded at Treasure Island, which is quite a 1D site, is influenced by the material properties over 1 kilometer away. And that's something that probably nobody wants to hear, because that says that when we're doing our ground response analyses, we probably need to be incorporating spatial variability into them from quite far distance from our actual site. So how does our approach compare with other ways that people use to account for shear wave velocity variability in 1D ground response analysis? So we investigated 5 methods: VS randomization, called Toro randomization; travel time randomization, which was proposed by Passeri and Sebastiano Foti; a surface wave approach, where we incorporate spatial variability from multiple VS profiles from surface wave testing; our H/V geostatistical approach, which I just showed you; and then changing the damping in the 1D ground response analyses. And I'm going to kind of cut this short in terms of explaining the shear wave velocity randomization. Suffice it to say that we have stochastic models where we can randomize shear wave velocity as a means to account for subsurface variability. This approach is used very commonly in probabilistic seismic hazard analyses for critical facilities. Through this Toro randomization approach, we can develop suites of VS profiles. For example, when we apply Toro randomization at Treasure Island, you can see that we're able to recover. There's 250 randomized VS profiles here in pink, and their median is a very close representation of the base case profile, which is measured using PS suspension logging. So the problem with Toro randomization that many have found is when you take the median of all of these 1D ground response analyses from the 250 VS profiles, you often get really excessive overdamping of high frequency response. And sometimes the variation in the fundamental frequency is so large that it causes your peak to be widened too much and not represent the true site response. So we applied shear wave velocity randomization at Treasure Island. We also use travel time randomization. And again, I'm running low on time, so I won't show you all of the details, but the travel time randomization worked quite well. It didn't overdamp the high frequencies, and it brought down the amplitude, the peaks in the theoretical transfer functions. In fact, some might say that it doesn't give you enough variability if you use the recommended parameters for the randomization, but it performed very well at Treasure Island. The surface wave approach, you can use numerous suites of shear wave velocity profiles developed from active and passive surface wave measurements, and you would only choose surface wave profiles that fit within the experimental bounds of your dispersion data and have approximately the correct fundamental site frequency. And when we applied that approach at Treasure Island, we used a bunch of different arrays, microtremor arrays up to 800 meter aperture, and several MASW arrays spread across different locations close to the borehole. And these are the shear wave velocity profiles that we developed from surface wave inversion. And when we studied the site response from those VS profiles from surface wave inversion, we found that they also performed fairly well and didn't overdamp the high frequencies. But perhaps there wasn't enough spatial variability in the area that we considered to bring down the amplitude of the theoretical transfer function. When we consider all of these methods, we already talked about the H over V geostatistical approach, so I'm going to skip that briefly here. I'm going to go to the last approach, which is increasing the damping. So normally we would use small strain damping in our linear viscoelastic ground response. And that small strain damping would be predicted from, say, the Stokey and Darendelli curves as a function of material type and confining pressure. But Tao and Rathje investigated increasing damping measured in the laboratory by 3 times and 6 times. And when we increase damping, we're able to bring down the fundamental peak in our theoretical transfer function, which better matches the empirical transfer function, but we've seriously overdamped the high frequency site response. So let me show you a summary of these results. So here we have Treasure Island, and you have in gray the empirical transfer function. This is the green line is the ground response from the single shear wave velocity profile measured at the site. We then look at the correlation coefficient and the transfer function misfit for that green line, and we enter and add the VS randomization profile. And you can see that by including shear wave velocity variability, we increase the correlation coefficient, but we actually decrease, or we make the transfer function misfit worse. So depending on the metric you use, you could say that we either improved the site response or we made the site response worse. When we use Passeri and Foti's travel time randomization, we increased the correlation coefficient and made it better. And we also reduced the transfer function misfit and made it better. So in this case, it worked quite well, the travel time randomization by Passeri and Foti. When we use the surface wave approach, we increase the R value, which is better, but we decrease the transfer function misfit quite substantially. And so there's somewhat mixed results saying that it could be better than the travel time randomization, but it could also perform not quite as well, depending on the metric you use to judge success. our H over V geostatistical approach, we get the best R value and the lowest transfer function misfit. So it performs extremely well. And when we do the damping modification, we increase R, but we do not significantly decrease the transfer function misfit. So again, there's kind of mixed results with damping modifications. I see that I'm virtually out of time. We've also done this at a different site, Delaney Park, which I don't have time to talk about. But in general, the approach that always works the best so far is our H over V geostatistical approach when we consider all reasonable methods of incorporating spatial variability. And I'm respectful of the time. I'm going to stop now and just say that we are working towards implementing these pseudo 3D models and actual 3D site response. And that's, of course, the ultimate goal. But because we can't perform 3D site response everywhere economically, the H over V geostatistical approach, I think, is really promising for still using 1D site response analyses, but being able to more realistically incorporate spatial variability. And with that, I will end the presentation. There's some references here for those who are interested. I'd like to acknowledge funding by Pacific Gas and Electric for this research. And if you need to get in contact with me, here's my contact information. So thank you very much for your time.
Thank you, Professor Cox. It was indeed a very nice presentation. Really, I enjoyed the lecture, your presentation, particularly some of the very interesting points which you brought out, highlighting the influence of the soil far away from the actual location where the ground response analysis is considered. And you have brought out with good data. And also you have compared with the low strain responses recorded and compared with that and showed that your approach has got a very promising future, particularly to ambitiously replacing the 3D ground response analysis with multiple 1D responses. It is interesting. It is interesting. And I request the audience and participants to have any questions for Professor Cox, who can now. We have 5 minutes for interaction.
It is question answer, sir.
Vijendra, there is a question in chat box. Please read this to Cox.
Okay. Yeah, I see the question.
Yeah,
I can read it. It says, when there is an inversely dispersive VS profile, so a profile with a low velocity layer in the middle, how do you generate the pseudo 3D model? And is the scaling of only thickness acceptable? The answer is probably not. We've investigated different approaches to scaling both VS and thickness, but it's non-unique. And so in cases where the velocity profile is more complex, you might have to spend a little bit more time making sure that you use, for example, boring logs to help constrain what you're doing using knowledge of local geology. And for an inversely, an inverse low velocity layer, you're probably going to have to be a little bit more careful because that's a situation where things may not be as simple. So, as in all things, there are simple cases and there are complex cases. And in the complex cases, you're just going to have to be a little bit more careful. But we find that if you develop a shear wave velocity profile that matches the fundamental site frequency, it's less critical that it's absolutely correct, as long as you have something that you are matching the site frequency that has reasonable layering and reasonable stiffness. I have another question. In the graph of the coefficient of R in area, the value of R is somewhere decreasing with the area and somewhere, so increasing and decreasing, correct? Can it be decided what would be the optimum area for the highest value of R? So we've studied that, and indeed, sometimes as we increase the area, we got slightly worse results until we increased the area to a certain point, and then the results got better again. We have to be careful about reading too much into the R value because it's only one metric of showing the goodness of fit. And what we found, and I didn't show this, is that the misfit continuously decreased as we incorporated more and more area. So while the R value fluctuated up and down a little bit, the transfer function misfit actually continuously decreased. And we talk about that in our paper, and I gave the references to the paper. They're at the end of the presentation.
Anybody?
Yeah, I have one.
Yeah, Professor Jack.
Yeah, Professor Cox, it is indeed an excellent presentation, very informative and also thought-provoking. What I'm saying is thought-provoking. Initially, yeah, I scared, frankly, like you said, 1D analysis is not going to work out. Even the anomaly at 1 kilometer can affect. So that is really scary. And then at the end, of course, you gave a solution. Wonderful. My query is like in the beginning, you told about the 3 approaches to come up with the pseudo shear wave velocity profile. That is essentially based on only the fundamental period. And finally, you adopted reducing the thickness of the layer. So in coming up that pseudo velocity profile, can't we use the amplification of HYV along with maybe the damping based on the thickness?
So yeah, there's one school of thought that says that we could invert the H over V data at every sensor location and develop a 1D velocity profile beneath each receiver, and that might provide some useful information. It's possible. I live in the camp, so to speak, where I do not completely believe that you can invert H over V curves to get a velocity profile. Because in my experience, which has been quite significant, the amplitude of the H over V curve can vary depending on which instrument I use, whether it's a broadband seismometer or say a 4.5 hertz geophone. It can vary depending on the coupling, whether I've set it on the ground or whether I bury it in the ground. It can depend on the noise, the strength of the noise. Sometimes it varies from day to day or from daytime to nighttime. And so I don't trust H over V amplitude as much as some people do. Some people trust it a lot. My experience has been that it's not extremely reliable, but if not, the frequency is usually very consistent. And so I prefer to trust the frequency and maybe use the amplitude as a guide. It's a good suggestion, but not to believe it too much, perhaps.
Very interesting. It seems there is a lot of scope for someone to explore how that amplitude can be varying, and with respect to whatever you said, instrumentation or the seasonal variation. Yeah, okay, thanks a lot.
You're welcome.
Anybody?
So I have another question in the chat. It says, do you filter the raw data that you get from the sensors? So yes, the empirical transfer function that we're calculating from the recorded ground motions, we only use a frequency range where we have a signal to noise ratio greater than 3 dB. And so we don't filter anything within that frequency range, which was about 0.5 hertz, a half a hertz, up to 10 hertz. But we filter everything outside of that frequency range, and we don't use that in the calculations of our transfer function misfit. So very low frequencies and very high frequencies we have filtered and not use those in our computations.
What was the fourth or fifth mode frequency of the Treasure Island down Olare?
The fourth mode frequency?
Yeah.
Let me
Is
quickly.
it
Oh, it's like less than 10 hertz. Yeah. So I'll quickly go to those results and I'll tell you real quick. So the fourth mode frequency at Treasure Island is only about 5 hertz. Yeah.
So
it's a pretty soft site. It's a really soft site.
Yeah. Filtering has not affected those modes.
That's correct.
Yeah, you just one follow-up question. Actually, in your presentation, you gave importance for higher modes. And most of the time, our primary structures are influenced by the fundamental mode. Maybe auxiliary structures, maybe, I'm not sure, but up to like, what is your take on the modes? Up to what mode one should go?
So we, like you said, the fundamental mode is most important, and we need to get that right for sure. After that, we need to start worrying about the higher modes, and depending on the stiffness of the structure, like for really soft sites, and if you have small structures, those higher modes can be very important, because if you have a stiff structure on a soft site, you know, you might have a really long period or low frequency fundamental mode, and you're never going to build a 30-story structure or a really long bridge on that site, but you're going to build some 4 or 5-story, you know, buildings, apartment complexes or whatever. And so those buildings that are shorter are going to be influenced by the higher modes. So we just need to be careful and not neglect the higher modes, because they can be important. And so fundamental mode is most important. And then after that, we have to start considering the match between those higher modes and the actual resonant frequency of our structure.
Thank you.
One last question, Professor Cox. In the pseudo velocity profile which you adopted to get the transfer function, what was the damping ratio used, minimum damping ratio used? Was it from Stokes, Darendelle?
Yes. That's correct. Yeah, so when we did our normal 1D site response analyses without modifying damping, we used d-min from Stokes and Darendelle, and so it varied as a function of material type and confining pressure. But you know, d-min would have typically been on the order of 1% to 2%, depending on whether it was clay or sand. And then when we modified damping using kind of Rathje's approach, we would take that d-min and multiply it by a factor of 3 or a factor of 6 in order to bring down the amplitude of the fundamental mode peak.
Sorry, Chair. One last question, just from my side.
Yeah.
Just one last question. Professor Cox, I couldn't able to understand whether it seems you used linear analysis. Am I right?
Yeah.
That is correct.
But why not? Normally we use equivalent linear analysis. What is the level of motions you used?
So when we chose our ground motions, and there's so much information, I didn't have time to present everything. We used only ground motions in this part of the study that had PGAs less than 0.05 G. Okay, so they were definitely in the linear elastic range. And we chose to do that because we want to study the impact of spatial variability without the overlapping complications of modeling nonlinearity. So we can do both, and we have done both, but we chose in this particular study to focus only on the impact of spatial variability, So we didn't have to study soil nonlinearity, which gets much more complicated.
Oh, wonderful. Excellent work. Very extensive and innovative. Thank you.
Thank you. Thank you. I appreciate the invitation.
Thank you, Professor Cox. Indeed, it really opened up the field for our young earthquake geotechnical engineers who are doing the research to look in this direction also, so that one-dimensional ground response analysis still has got some value, which is in recent times has got some negative remarks. Okay, you have brought back its due respect to it. Thank you for that.